Hello everyone. Today I'm going to cover randomization. I'm going to cover the topics: introduction to program evaluation, introduction to RCT, and previous paper on the effect of class size for test scores, and practical problems and warning experiments. And next week, I'm going to cover these three papers. First paper is about private schooling in South Korea, and second one is about the warming project in Kenya. The last one is about discrimination in the US. For today, I'm going to cover randomization. And remember that the last year, the Nobel Prize in Economic Science was awarded to three economists, Abbas Banerjee, S. Duflo, and Michael Kramer, for their experimental approach to alleviating global poverty. And they started a new way of doing research about poverty. Especially, they tried to divide up the big problem of global poverty into smaller questions. And they tried to answer these questions by using field experiments. And I'm going to show one of those papers next week, Michael Kramer's The Dewarming Project in Kenya. And their research has influenced public policy. Their new research has helped governments and organizations like ADB World Bank to choose more effective methods for fighting poverty, and hope today's lecture would help you to understand the randomization. And first, I will start with the terminology. An experiment is designed and implemented consciously by human researchers. An experiment randomly assigns subjects to treatment and control group, like think of clinical drug trials. And a quasi-experiment or natural experiment has a source of randomization that is as if randomly assigned. But this variation was not the results of an explicit randomized treatment and control design. And program evaluation is the field of statistics and economics aimed at evaluating the effect of a program or policy. For example, an advertisement campaign to cut smoking or job training program. So here I show different types of experiments. Clinical drug trial. The question is, does a proposed drug lower cholesterol? Outcome variable is cholesterol level and X is treatment, dummy or dose of drug. Or job training program, then outcome is an indicator for having a job or not, or wage income. And X means whether they went through training program or not, like dummy. Or class size effect, especially Tennessee class size experiments. Today I'm going to cover this topic very soon. And outcome variable is test score, like Stanford Achievement Test. And X is class size treatment group, regular or small, each dummy. And potential outcomes and causal effects. A treatment is expected to have causal effect for a given individual. Given individual, the treatment and something happens, which is different, possibly different than what would happen if he or she didn't get the treatment. The potential outcome is the outcome for an individual under potential treatment or potential non-treatment. For an individual, the causal effect is the difference in potential outcomes if he or she does or doesn't get the treatment. But the individual's causal effect cannot be observed because once he or she gets the treatment, we don't observe his or her status of being not treated. That is, he or she cannot have both the treatment and non-treatment at the same time. So that's the missing counterfactual problem. Example, a child with good drinking water has fewer sick days than the same child would have if he had bad drinking water. But this is impossible because we only observe individuals in one state. Once he drunk good drinking water, then we cannot observe his status of drinking the bad water. That's a missing counterfactual problem. Here, let D equals to 1 or 0, the treatment indicator for the ith individual. When treated, D equals 1. When not, D equals 0. And let Y sub 1 be the outcome if treated, and Y not, Y sub 0, be the outcome if not treated. Then the impact for the individual is Y1 minus Y naught. But as mentioned before, this is impossible as we only see this individual in treatment or control at any given point in time. Empirical research in social sciences, especially economics, in particular, suffers from a major problem, which is missing counterfactual. Individuals or firms can usually not be observed with and without treatment at the same time. So we cannot get individual treatment effects. Instead, we can compare affected people and non-affected people. But correlation is not causation. And how do we get treatment parameter? So average treatment effect on the treated ATT or ATT, impact of treatment on those treated is expectation y1 minus y not given d equals 1. And we can decompose this expectation to expectation y1 given d equals 1 minus expectation y not given d equals 1. From data, we can observe the first term, expectation of y1 given d equals 1, that is sample average of observed outcome in treatment group. But we cannot observe the second term. This is missing counterfactual. Expectation of y naught given d equals 1. Then the question is, can we use the expectation of y naught given d equals 0 instead of the missing counterfactual? Because individuals decide not to participate in the program, then we can easily observe y naught, potential outcome of not treated. But they are not the same. Selection bias, right? Here's the example. A lot of language in the experimental and quasi-experimental literature is borrowed from the medical literature. Simple example, introducing notation and the selection problem. Do hospitals make people healthier? And data from National Health Interview Survey 2005, health status was measured from 1, poor health, to 5, excellent health. So if you take a look at the table, then the means of health status for two groups, hospital group and non-hospital group. Hospital group's mean health status is 3.21, non-hospital group's mean health status was 3.93. And the difference between these two is 0.7. And if you calculate the t-stat, then the difference between these two groups is quite significant. Then can you conclude that hospitals make people like sick? Think of hospital treatment as a binary random variable. D equals 0 or 1. An outcome of interest here, health status, is denoted Y. The main question is Y affected by hospital care? For each individual, there are two potential outcomes. If D equals 1, if they went to the hospital, then the potential outcome is Y sub 1. And if we had not gone to hospital, then the potential outcome is Y not. So I put some explanation for those two potential outcomes, Y1 and Y not. An individual causal effect of hospital treatment is Y1 minus Y not. And the observed outcome Y can be written in terms of potential outcomes as Y equals Y naught plus Y1 minus Y naught times D. This is quite parsimonious way to show the potential outcome. For example, D equals 0, then only Y naught remains. And if D equals 1, then the first and the last term cancel each other, so only Y1 remains. And this is quite useful because Y1 and Y1 minus Y naught is the causal effect of hospitalization. But the fundamental problem is that we cannot observe both Y1 and Y naught for each individual. So we therefore have to estimate the average effects of hospitalization by comparing average health of those who were and those who were not hospitalized. What are we actually measuring if we compare this average? So first row, expectation Y1 given D equals 1 minus expectation Y0 given D equals 0. This is observed difference in average health. And both terms we can easily observe, right? There's no missing counterfactual. In the second row, I subtract and added expectation Y0 given D equals 1. First I subtract and then add the same term. So which is same as the first row. And then the first two terms is actually ATT, average treatment effect on the treaty. And the remaining two terms is a selection bias. The thing is that the question is that how to remove the selection bias in this equation. So the answer is here, random assignment solves the selection problem. Random assignment of D makes treatment D independent of potential outcomes Y. So participants, sample, individual, did not have any choice of like being treated or not treated. They didn't have any choice. It's randomly assigned. They are randomly assigned to treatment and control groups. The selection bias term above was expectation Y0 given D equals 1 minus expectation of Y0 given D equals 0. And if D is independent of Y because of randomization, then we can swap expectation of Y0 given D equals 1 for expectation of Y0 given D equals 0. then the selection bias term disappears with random assignments. Then ATT is here. Expectation y1 given d equals 1. Expectation y0 given d equals 0. Then second term can be replaced with the expectation given y0 given d equals 1. Then actually using the feature of the expectation sign, we can make it expectation y1 minus y0, which is ATT. Here's an example. The two columns for whether they have health insurance or not. If they have health insurance, then d equals 1. If they do not have health insurance, then d equals 0. And the second rows show the medical spend with insurance and medical spend without insurance, respectively. And underlines like $1,000 and $500, this is observed from data. And not underlined, $800 and $700, not observed. I mean, this is hypothetical situation. And naive estimator is y1 minus y0. I mean, expectation of y1 given d equals 1 minus expectation of y0 given d equals 0, which is $500. But if we are really interested in measuring the ATT or ATT, then it should be expectation of y1 given d equals 1 minus expectation of y0 given d equals 1, which is $200. So the naive estimator actually overestimates the real effects of health insurance on medical spending. So I made it as a hypothetical situation, but if you're interested in this kind of example, then please read the paper by Finkelstein et al. In the syllabus. Then how do researchers learn about counterfactual states of the world in practice? In many fields, evidence about counterfactuals is generated by randomized trials or experiments, for example, medical research. And if you want to do randomization, then you have to give all equal chance of being in control or treatment groups. And also, randomization guarantees that all characteristics will be on average equal between groups because participants are randomly assigned between control and treatment group. So if you have more and more sample, then the bigger sample size, then they should be quite similar to each other, except for the intervention. Only difference is the intervention. And randomization for causal inference has two stages. The first stage, a random sample of units is selected from a defined population. And second stage, the sample of units is randomly assigned to treatment and comparison groups. The first stage is about sampling issue, and second one is the randomization. So first stage is also very important because if suppose that you are interested in studying the effect of some policy in South Korea, but if you select sample from the US, Australia, then it's not representative at all. Also, your sample is only composed of only the people from Seoul, not Daegu, Busan, Jeju. Then your sample is also has some problem of representativeness. You have to pick individuals all of the places according to based on the city's population density. Here, out of eligible population, you have to pick sample randomly. And if you have sample, then you have to randomly assign the sample into treatment or comparison groups. I already explained it just a second ago. First stage ensures that the results in the sample will represent the results in the population within a defined level of sampling error. This is for external validity. And second stage ensures that observed effect on the dependent variable is due to the treatment rather than to other confounding factors. This is for internal validity. So both stages are quite important. Think about unit of randomization. There are many levels of units in the data, like district level, village, family, school, individual, for example, child. The level of randomization determines the power of the trial. More units in the treatment and comparison groups, then estimate of difference between treatment and control group becomes more precise. This is related to the standard errors. If you have more sample, then standard error will reduce, so you can more precisely estimate. But at the same time, the lower the level, the more potential for contamination. Children in a class, families in a village, hard to control. And also the lower the level, the harder to administer the program. In general, choose the lowest level that is administratively feasible. I mean, instead of using district village level, it'd be better to use like the class level, the family, household, individual. But it depends on context. So we can also discuss this issue later. And here, empirical strategy, random assignment. An ideal randomized controlled experiment randomly assigns subjects to treatment and control groups. Let X be the treatment variable, like dummy variable D, and Y the outcome variable of interest. If X is randomly assigned, for example by computer, X is independent of all individual characteristics. So in the regression model, Y equals beta naught plus beta 1x plus U error term. If X is randomly assigned, then X is independent of error term U. So expectation U given X should be 0, or variance X and U should be 0. Then OLS yields an unbiased estimate of beta 1. Because there's no indigeneity issue in the perfect randomization. And the causal effect is the population value of beta 1 in an ideal randomized controlled experiment. And there are pros and cons of RCT. So if we do have RCT, then so we have exogenous variation, so no selection issue in the estimating the effect of some policy and clear treatment effects. Also, we can use easy OLS because as I mentioned before, the expectation of error term given X is 0, so beta 1 is always the causal effect. At the same time, there are many problems, concerns. So randomization bias, the experimental participants are different from non-experimental participants. It's because of that, it's hard to generalize our results to the general population. And substitution bias, control get some other treatments, In Hawthorne effects, participants change their behavior because they knew they are in the experiments. In non-random effect, the best or worst more likely to drop out, especially the attrition rates between the comparison and treatment groups are different, then we might end up with some problem, especially non-random attrition. I'm going to go over these threats of RCT in a coming lecture. But why is that experiments? Ideal randomized controlled experiments provide a tool for policy evaluation and a conceptual benchmark for assessing observational studies. And actual experiments are rare and very expensive, but at the same time, it's quite influential. As I mentioned before, the three economists, they got the Nobel Prize in economic science because of, their contribution to the new way of research. And experiments can overcome the threats to internal validity of observational studies, but they have their own threats to validity. I'll go over these threats in a minute.